Hello and welcome to lecture 21 of analog integrated circuit design. In the previous class, we have looked at components available on a CMOS process, that is the commonly used components like the resistor and the capacitor. We will be studying the transistor in this class. What we learnt was that the resistor and capacitor parameters can vary significantly over process. These are known as process corners, but if you make two identical resistors, they will have identical value, and if you make two physically identical capacitors, they will have identical value, and so on. Okay. Now, we also saw that despite this being nominally identical, there will be some small mismatch, and the amount of mismatch is related to the absolute physical size of the device. If you make a pair of physically large resistors, then they will match very well to each other. If you make them very small, then the matching will be rather poor. Okay. Now, we saw quantitatively how to relate the standard deviation of mismatch to the physical size of the resistors and capacitors. Okay. This large variation in absolute value is known as process variations, okay, and physically identical components will have closely matched values, and the relative mismatch is related to the physical size, the standard deviation of delta r by r, that is the difference in the value of between a pair of resistors to the nominal value of the resistor r naught, which is usually called sigma r, is given by a r by square root of W L, where W and L are dimensions of the resistor. Similarly, delta C, the difference in values between a pair of nominally identical capacitors to the mean value of the component is sigma C, and that is given by A C by square root of W L. And A C and A R will be given to you by the process foundry. Based on this, you can figure out exactly how big to make the resistor or the capacitor. Okay. We will see later that this is true not only of resistors and capacitors, but also of all other components. They all have a similar behavior with mismatch. If you want closely matched components, you need to have physically large components. Okay. Finally, we need to have identical layout environment for good matching. This means that you may have to use dummy devices, orient all the devices in the same way, and perhaps use even common centroid layout and so on. Okay. So, to get the very best matching, you need to do all of these things. What we will do in this class is to look at the more sophisticated component which is available in the CMOS process, that is the MOS transistor itself. We will discuss the model of the MOS transistor, both large and small signal models, look at the mismatch, and see how to use it in the circuit that we are going to design. Okay. Now, in the CMOS process, we will have two types of MOS transistor. First of all, most CMOS processors are built starting from a PMOS substrate, and on that you build an NMOS transistor like this, Okay. This is the gate, drain, source, and the bulk itself or the body will be like that. Okay. Now, if you have two transistors, two NMOS transistors, you can see that the bulk is common to both of them, and we need to keep all of the bulk source and bulk drain junctions reverse biased, because these drain and source junctions are there only to make connection to the channel that will be formed between them. Okay. These PN junctions should not be forward biased. So, this means that typically you are constrained to connect the bulk of the NMOS transistors to the lowest voltage on the integrated circuit. Okay. NMOS bulk, which is basically the substrate, common substrate connected to the lowest voltage on the IC. Okay. Now, because of this constraint, we also have to look at what happens to the transistor when the bulk voltage is different from the source voltage. Okay. Now, there is a variant of the process which is known as a triple well process. In this case, you can have NMOS transistors with isolated bulk nodes. Okay. So, if you do have a triple well process, what happens is you will have some situation like this. You will have an N well, and in that you will have a P well. Okay. Now, because the P well inside has no connection to this one, the bulk of the inner transistor can be connected independently of what happens to the substrate of the outer transistor. Okay. So, in this case, this bulk here need not be connected to the lowest potential, you can connect it to whatever potential is required for the proper operation of that transistor. Okay. But most of the processes that are commonly used are not triple well processes, and you will be forced to connect the NMOS transistors bulk to the lowest voltage on the chip. Okay. That is something to keep in mind while designing the integrated circuit. Now, we can't design with only NMOS, or we could, but the design would be rather inefficient. It is better to have both NMOS and PMOS transistors. To have PMOS transistors, we have an N well, okay, and inside that you make the P plus drain and source connections, and you will have a PMOS bulk connection to the N well. Okay. So, this is a PMOS transistor and that is an NMOS transistor. So, the PMOS transistor is formed inside an N well. Okay. Now, because you make all the components on a common substrate, there is something common electrically to all of them. Okay. Those are the things that we need to understand. In discrete component circuits, every component is separate. Okay. If you have two transistors, they will be in separate packages and there really is no communication between them, so to speak. Whereas, on an integrated circuit, if you have 100 transistors, they all share a common substrate. So, they will in some way talk to each other, there is something common to them. Now, in order to isolate them, we need to take care of some things. One of the things that we do is to connect the substrate to the lowest potential on the chip. Okay. Now, this also means that the model that you use for the MOS transistor should model the effect of this substrate voltage or the bulk voltage on the transistor. We will first review the MOS transistors large signal model. The model is similar for NMOS and PMOS transistors, and then we will go on to the small signal models. Okay. So, if I consider an NMOS transistor, there are 4 terminals really, and physically they correspond to these terminals, and this is the bulk. Okay. It is not our goal here to discuss in detail the physics of the MOS transistor. We will only study the models to a sufficient extent that we can use them for circuit design. Now, one thing you will observe is that from the layout as well as from the symbol, the drain and source are interchangeable. Okay. The device is symmetrical with respect to drain and source, and that is true in reality. We do label one of them the drain and the other one the source, and what makes the distinction is which voltage is higher. Okay. It is not related to how the device is fabricated. Now, it is quite common to model the current that goes from the drain to the source as a function of the gate source voltage, the drain source voltage, and the bulk source voltage, or sometimes the opposite of it, the source bulk voltage. We will see what the model is. Now, the symmetric structure of the MOSFET means that perhaps it would have been more sensible to model the device by referring all the voltages to the bulk, and there are such models which are symmetrical and nice, but it has been a long held convention that things are usually modeled by referring to the source in analog circuit design. So, we will continue to use that. So, the current ID which goes into the drain and comes out of the source, it turns out that the gate current and bulk current are negligible in most cases, is given by mu on Cox by 2 W by L VGS minus VT square 1 plus lambda VDS. Okay. This is the model when VGS happens to be more than some parameter VT, the threshold voltage, and the drain source voltage is greater than VGS minus VT. Okay. This is known as the saturation region. The current equals mu on Cox W by L VGS minus VT times VDS minus VDS square by 2. This is the case when VGS is more than VT and VDS is less than VGS minus VT. This is known as the linear or the triode region, and also the current will be 0 when VGS is less than VT. Okay. And implicit in all of these things is that VDS is greater than 0. That is why we identify one terminal as the drain, the other one as the source. If this happened to be more than that, then we would call this the drain and that the source. Okay. So, VDS greater than 0 is common to all of these things, and when the current is 0, this is called cutoff when VGS is less than VT. Okay. You are probably already familiar with this model from the basic electronics course. This will be a quick review of the MOSFET model. Okay. Now, graphically what does this look like? We can plot ID versus VGS for a constant VDS. So, this model says that the current is 0 up to a voltage called the threshold voltage, and after that it increases as a parabola. Okay. And if you plot ID versus VDS, what happens is when VGS is less than VT, the current is almost 0, and when VGS is greater than VT, in the triode region the current increases and in the saturation region it increases very slowly. Okay. Something like that, and this boundary between the triode and saturation region follows a parabola. In fact, it is the same curve as this shifted to the origin. By the way, this is the current in saturation region. Okay. Now, because it is in saturation region, the current does not vary too much with VDS. It does vary, but not greatly, because the slope here, the slope in this region is very small. Okay. So, on this curve, this is the saturation region and this is the linear or triode region. Okay. I am assuming you are familiar with these MOS characteristics. I will only discuss things that are slightly unfamiliar from basic courses. Now, what it says is that in the saturation region the current is almost constant, it is independent of VDS. It is dependent on VDS through this parameter lambda, but this lambda is a small number. So, the current can be thought of as almost independent of VDS, and that is why we use it as a current source. Okay. Later we see that for most amplifiers we would like our transistors in the saturation region. Okay. The linear or triode region is also useful, and for a certain portion of the region when VDS square is very small compared to the other term, we will have linear dependence between ID and VDS. So, it can be used as a resistor. Okay. And also when you use the MOS transistor as a switch, it will operate between deep triode region where VDS is almost 0 and cut off when there is no current at all. Okay. Now, one of the things we should keep in mind is that the threshold voltage Vt itself is dependent on VSB, okay, or VBS. VBS is nothing but minus VSB. You see that so far in our expressions the bulk source voltage VSB has not appeared in the picture, but it will indirectly through the threshold voltage Vt, and Vt is given by some Vt0, which is the threshold voltage when VSB equals 0 plus some parameter gamma times square root of VSB plus 2 phi f minus square root of 2 phi f. Okay. We will not discuss this equation in detail. Vt0 is nothing but the threshold voltage with 0 VSB, and you can see that the threshold voltage increases with VSB. You can refer to some device textbook for the meaning of gamma and 2 phi f and so on, but for us right now we will only focus on the fact that the threshold voltage increases with VSB. Okay. Now, what does this mean? Let us try and make intuitive sense of these model equations that we have written so far. First of all, the saturation triode boundary. What does it mean? I think again you will be familiar with the operation of the MOS transistor from basic devices courses. This is the NMOS transistor. Okay. You know that if you tie drain and source together so that these two are at the same potential, and then you go on increasing the potential of the gate, what happens is below the gate you will form an inversion layer, and around here you will have a depletion layer, okay, with fixed charges. And in this you will have the inversion layer, and the inversion layer is what is responsible for conduction of current in the MOS transistor. Okay. Now, the amount of voltage you need, let us say we have the gate and source tied together, the amount of voltage you need between the gate and drain or source to start the process of inversion is the threshold voltage. Okay. Vt is nothing but VGD, which is the same as VGS with this connection, required to form the inversion layer. Okay. Now, what is happening when you have Vd not equal to Vs? Let us say we do not have this connection. This is the normal case in a circuit. The drain voltage can be quite different from the source voltage. Okay. Now, let us imagine a case where a drain voltage is larger than the source voltage. What happens? The inversion layer will be thicker at the source side, okay, and thinner at the drain side. Okay. It will look something like that. Now, Vd greater than Vs means that there is less voltage across the oxide at the drain side than at the source side. Okay. It also means more inversion at the source end compared to the drain end. Okay. Now, what was the condition for saturation? We said that Vds has to be greater than Vgs minus Vt. In other words, Vd is greater than Vg minus Vt. I will remove the common source reference from Vds and Vgs both, or Vg minus Vd is less than Vt. Okay. Basically, the voltage across the gate and the drain, which is basically the drain end of the channel, is less than Vt. So, what it means is that in saturation region, the drain end of the channel is not inverted, whereas the source end is inverted. That is, the channel is pinched off at the drain. In fact, if you recall from device physics courses, that is how we get the square law model. You assume that there is a pinch off, and then from there you can get the square law dependence of the current on Vgs. Okay. Now, what happens in triode region? In triode region, both the drain end and the source end are inverted, and the channel is continuous all the way from source to drain. And when Vds equals 0, which is the lowest Vds you can have, you can say that this is the deepest you can go into the triode region, then we will have a uniform channel from the drain to the source. Okay. In saturation, the drain end is not inverted, and in triode region both the ends are inverted. Okay. So, that is one thing to keep in mind. Now, this also tells you once the drain end is pinched off, the drain will not have a significant effect on the amount of charge in the channel, and that is why we get this constant current in the channel when the transistor is in saturation region. Okay. So, you start by inverting both ends, and then you raise the drain potential to a point where the drain end is no longer inverted, then the drain voltage does not have significant effect on the channel charge, because it is not even connected to the channel. So, now you will have charge and consequently a current that is independent of the drain voltage. Now, it does turn out that it has a minor influence, and that is why we have the small slope lambda. Okay. Now, effect of the source bulk voltage. So, first of all, again if you recall the basic operation of the MOS transistor, what happens is that you start with a piece of semiconductor, which means that it does not really normally conduct. Okay. There is no conduction layer between the drain and the source sides. Let me call this the drain and this the source, that is the gate. Okay. Now, the very basic principle can be thought of as you have a capacitor between gate and this point, okay, gate and this region of the MOS transistor. If you raise the voltage across the capacitor sufficiently, you will form charges in the semiconductor, and that can be used for conduction. Okay. Now, actually if you observe this, there is not one capacitor, but two. Okay. First of all, there is the capacitance between the gate and the channel, and also there is a capacitance between the bulk and channel across the depletion layer. Okay. So, you can think of it as having the capacitor from gate to the channel. Now, the thickness of this oxide is T ox and the capacitance of this per unit area epsilon ox by T ox is what is known as C ox. Okay. This appears in the expression for the current, as you well know. Also on the other side you will have the capacitance of the depletion region, okay, basically the capacitance of this region, right. Now, clearly if you raise either the bulk voltage or the gate voltage, the channel charge will be influenced in the same way. Okay. Now, imagine that the channel is fixed to some potential, you increase the bulk voltage, there are negative charges on this plate of the capacitor, which is basically the increase in the channel charge. If you increase the gate voltage, again there are negative charges on this plate of the capacitor, which corresponds to an increase in the channel charge. So, whether you increase the gate voltage or increase the bulk voltage, qualitatively the same thing is happening in the MOSFET. There are more charges in the channel, okay, and once you have more charges in the channel, you will have more charges available for conduction and the current will tend to increase. Okay. So, that is why this bulk is also many times called the back gate, and there are even circuits which use the back gate like the normal gate that we use. Okay. Now, earlier I did not mention what the W and L in the MOSFET were. As usual, this is the gate, source and the drain, and the distance between the drain and source is the length of the transistor. And if you look at the top view of this device, there is a certain width for the source and drain regions. Okay. So, the current flows across this width, okay, and that is the width of the MOS transistor. Okay. Now, it turns out that if you double the width, it is like connecting two MOSFETs in parallel. Okay. Let us imagine a case where you have two MOSFETs with the same VGS, VDS and VBS, the same voltages everywhere, and then you put two MOSFETs next to each other, the currents in them just add up. That is why we get the proportionality of the current to the width of the transistor. Okay. If you increase the width, the currents will increase proportionately. So, that is the basic large signal model of the MOS transistor. Okay. Now, I said that increasing either VGS or VBS increases the current, okay. And the equations that we had were mu 1 C ox by 2 W by L VGS minus VT square times 1 plus lambda VDS. This is the current in the saturation region. The principle is the same in the triode region as well. and the threshold voltage itself is given by V T naught plus gamma square root of V S B plus 2 phi f minus square root of 2 phi f. Okay. Now, this equation is written in terms of V S B, but you see very easily that if V S B increases, the threshold voltage increases, okay, and if the threshold voltage increases, the current reduces. So, finally, the conclusion is that if V S B increases, the current will reduce, which is the same as saying if V B S increases, the current will increase. Okay. V S B is the variable of choice because V S B is always positive in an NMOS transistor, and this is because we would like to keep that source bulk junction reverse biased. Okay. We do not want to turn on those diodes. The reason the junction is there is to make connection to the channel. If we turn on those diodes, those currents will interfere with the normal operation of the MOSFET. They can cause some undesirable effects in the operation of the chip. Okay. So, because V S B is always positive, the equations are always written in terms of V S B, not V B S, but you can easily see that if V B S increases, the current will increase. Okay. So, we have to consider the effect of all 4 terminals on the current in the MOS transistor. We have already looked at the large signal model, and we will use this model as a sort of guideline for our design. Now, it turns out that the actual model of the MOS transistor that reflects the operation of a modern MOS transistor is really complicated. What we will use this very crude model for, the level 0 model for, is to gain some insight into the operation of the circuit. Okay. At this point, again let me rewrite the expression for the drain current. Now, this expression says that ID is directly proportional to W and ID is inversely proportional to L. Okay. Now, the current turns out to be directly proportional to W because there is a conduction current flowing across a width of W. Now, if you increase the W, the length across which you have a flow of current will increase. That is why if you have W that is doubled, that is like having 2 transistors in parallel and the current will also double. So, this means that the proportionality to W is more or less exact. Okay. Now, if you take a real MOSFET and if you double the width of the transistor, you will find that the current will approximately double. Okay. Now, the inverse proportionality to length comes under a more restrictive condition. It comes about because the field in the MOS transistor is reduced. Okay. But because there are lots of non-ideal effects that make the MOS transistor current not exactly inversely proportional to L. Okay. You cannot rely on this inverse proportionality. So, what I mean is the following, right. So, let us say you have a certain MOS transistor. I think you are all familiar with current mirrors. Okay. Let me take 2 cases where first of all I have a diode connected transistor here. We will deal with these circuits in detail later. I just want to illustrate a point here. So, let us say I inject a current I naught. Now, let us say I want 2 I naught and 2 I naught here. Okay. And let us say the aspect ratio of this is W by L, that is the width of this transistor is W and the length is L. Okay. In fact, to make it explicit, let me not write W by L, I will write W comma L. Now, let us say I want 2 I naught, there are 2 ways of getting it. I can make 2 W and L, or I can make W and L by 2, okay, assuming that L by 2 is above the minimum possible length of the transistor in the given process. Now, you will find that this 2 W by L will give you almost 2 I naught, whereas W and L by 2, the current in this branch can be very far from 2 I naught. Okay. So, you would never ever want to do something like this. If you want, let us say, a current mirror or a number of identical transistors whose currents have to be scaled. Okay. When I say identical, they are identical in all respects except for a scaling of current. You should scale only the W and not the length of the transistor. Okay. So, for instance, when you make a current mirror and you want a ratio of let us say 2 to 1 or 4 to 1 or whatever it is, between the input current I naught and the current that you want in a particular branch, you should scale the width of the transistor accordingly and not the length. Okay. In fact, if you want close matching between any pair of transistors, they should have the same width. We will see how to arrange the transistors layout so that that happens later. Okay. So, you use ratio of widths for multiplying currents, you never use ratio of lengths. Okay. So, that is the brief overview of the large signal model of the MOS transistor. Okay. We have used the NMOS transistor for illustration, but I will very quickly go through the PMOS transistor and show that it is exactly the same way. Okay. A PMOS transistor symbol is like this when we include the bulk. This is the bulk, source, drain and gate. Usually the source is drawn above the drain because the source potential is higher than the drain potential usually in a PMOS transistor. And in a common integrated circuit, you have the P substrate, the N well and the PMOS transistor inside. Okay. And that is the bulk. Now, the equations are exactly the same, except that we will write them in terms of VSG, VSD and VSB. Okay. So, ID which flows from the source to the drain is given by mu p Cox by 2 W by L VSG minus VT P square, and this is when VSD is greater than VSG minus VTP and VSG itself is greater than VTP. Okay. This corresponds to the saturation region in the PMOS transistor, and in the linear or triode region we will have here we will have okay. And finally, we will have 0 current when VSG is less than VTP. Okay. So, these correspond to the triode and cutoff regions respectively, right. Now, the equations are exactly same as that of the NMOS transistor, and the expression for the threshold voltage is also the same. Okay. The PMOS threshold voltage will be the threshold voltage with 0 bulk source voltage plus gamma times square root of VBS plus 2 phi f minus square root of 2 phi f. Okay. Now, compared to the NMOS transistor, there are many ways of writing the PMOS equations. In some books and references, the threshold voltage is negative, and you refer to VDS and VGS, which are negative voltages. What we have done is, in our notation, the threshold voltage is positive, and we also refer to voltages VSD and VSB, which are positive. Okay. Again, for the NMOS transistor, the threshold voltage is positive as well. Now, these are known as enhancement transistors, the transistors in which the threshold voltages are positive and this is the most common type of transistor. So, that is what we will assume we will have. Okay. Just little more discussion on the regions of operation in the NMOS and PMOS transistor. Because we have to keep calculating this all the time in circuit design, it is extremely important to become very familiar with this. Okay. This is the symbol that is used for the NMOS transistor, and sometimes the bulk is tied to the source. Okay. And in this case, many times a 3 terminal symbol is used just for simplicity. Okay. And you can see that if the bulk is tied to the source, the threshold voltage equals VT0, the threshold voltage at 0 value of VSB, and we can think of it as a 3 terminal device like this with Vt equal to Vt0. Okay. Similarly, for the PMOS transistor, sometimes the bulk is tied to the source, it is like this, and in this condition we can represent the PMOS also with a 3 terminal symbol, where this is the source, gate and drain. Okay. Now, what does it mean for the transistor to be in saturation or in triode region? First of all, in the normal operation of the transistor, I will use the 3 terminal symbol for simplicity here. There will be a VGS which is greater than Vt. I do not necessarily mean that there will be a voltage source connected between gate and source, but whatever is connected will establish a VGS that is greater than Vt. Okay. Now, if this voltage becomes very small, okay, between drain and source, the transistor will go into triode region. You can imagine that when these two are squeezed together, the current keeps getting smaller and smaller. Okay. So, as the drain voltage comes closer to the source voltage, the current gets smaller. And exactly the same is the case in the PMOS transistor as well. We will apply a VSG that is more than the threshold voltage, and if the drain voltage comes too close to the source voltage, if the drain voltage increases and comes too close to the source voltage, then it will tend to go into the triode region, and if the drain and source voltages are the same, the current will be 0. Okay. There will be no voltage across the device, that is somewhat similar to having 0 voltage across a resistor, which gives you 0 current. Okay. The reason I am mentioning this is sometimes there is confusion about whether it goes into triode region if the drain voltage decreases or increases, and especially what happens in a PMOS. So, if these two terminals come close to each other, they tend to go towards the triode region, okay, whether it is PMOS or NMOS. So, that is one way to think about it. Another way is we can write the expression for triode versus saturation region in two different forms. For an NMOS transistor, VDS should be greater than VGS minus VT. It can also be written as VD greater than VG minus VT. All I have done is to add the source voltage Vs to the two sides. Okay. Now, this form is sometimes convenient because we are not calculating VDS and VGS, we are simply comparing the drain voltage compared to the gate voltage. So, what is this saying? Vd has to be greater than Vg minus Vt. So, this voltage has to be larger than Vg minus Vt. So, because the Vt is positive in our transistors, the drain voltage can go below the gate voltage, but not by more than one threshold voltage, that is what it is saying. Similarly, in this case VSD has to be greater than VSG minus Vt, which basically says that minus Vd greater than minus Vg minus Vt, or Vd has to be less than Vg plus Vt. So, as the drain voltage goes on increasing, it can go above the gate voltage, again Vt is positive, but it cannot go above by more than one threshold voltage. That is also a good way of thinking about triode versus saturation region. So, there should be no confusion in this regard, because we will soon move to circuits which have many tens of transistors, and you should be able to quickly tell which transistor will go into triode region when. Okay. As we will see later after we discuss the small signal parameters, we would like to keep all our transistors in saturation region for proper operation of our amplifiers most of the time. Okay. This phenomenon of the VBS influencing the current or VSB influencing the current is known as body effect. Okay. Now, one last comment on the currents in a MOS transistor. So far we have assumed that if VGS is less than Vt in an NMOS transistor or VSG is less than Vt in a PMOS transistor, the current is 0. That is, if the gate source voltage is below the threshold voltage, the current will abruptly turn to 0. Okay. Now, in reality this is not so. Okay. The region of VGS being greater than Vt in an NMOS or VSG being greater than Vt in a PMOS is known as strong inversion. Okay. And the square law that we have for the MOSFET that we are all familiar with is true when the MOSFET is strongly inverted, but it turns out that when VGS is less than Vt in an NMOS transistor, the current will not fall to 0. Okay. It is still non-zero. The current will be small, the current will be smaller than in strong inversion, but it will not be exactly 0, and it turns out that the current follows an exponential relationship. Okay. This is similar to that of a bipolar transistor, where this Vt is kT by Q, which is 25.9 millivolts at room temperature, is the thermal voltage. Okay. So, it goes from being a square law device to an exponential device. We will not go into the exact details of what is in I naught, but just like in the strong inversion region, I naught happens to be proportional to the width of the MOS transistor. Okay. We will not go into the details, but we will just keep in mind that the current will be an exponential, and we will see later that this is in fact a very useful region of operation for certain applications. We will discuss that after we discuss the small signal model of the MOS transistor. Thank you.